Quick note, these two are correct ways of writing negation of P.
Let's take a look at the conditional statement P implies Q. Starting with the statement P implies Q, we can form three new conditional statements, which are Q implies P, not Q implies not P, not P implies not Q. Here, Q implies P is called the converse of the conditional statement P implies Q. Not Q implies not P is a contrapositive of P implies Q. Not P implies not Q is the inverse of P implies Q. Now the question is, does all of these three conditional statements has always the same truth value as P implies Q? Turns out that only the contrapositive has the same truth value always as P implies Q. So P implies Q and not Q implies not P are equivalent because they always have the same truth value. We can check it out using the truth table. We can draw the truth table for P implies Q and not Q implies not P. And we can see that for every possible values of P and Q, both P implies Q and not Q implies not P has the same truth value. When two compound propositions always have the same truth value, we call them equivalent. So that a conditional statement and its contrapositive are equivalent. With a similar observation style, we can also conclude that the converse and inverse of a conditional statement are also equivalent. Means Q implies P and not P implies not Q are also equivalent. Now let's work out an example. We have a conditional statement here. That is, the home team wins whenever it is raining. This is a conditional statement. We are supposed to write the contrapositive, converse and inverse of this conditional statement. Let's do it. If you see, it is of the form Q whenever P, where Q represents the home team winning. P represents the statement it is raining. So Q whenever P is one of the ways to express the conditional statement P implies Q. We already know this fact from our previous lecture. Now, the original statement can be rewritten as if it is raining, then the home team wins. Consequently, you can write the contrapositive of this conditional statement as if the home team does not win, then it is not raining. The converse is if the home team wins, then it is raining. What about the inverse? If it is not raining, then the home team doesn't win. Now let's see about biconditional statements. Let P and Q be propositions. Biconditional statement is a proposition P if and only if Q. This biconditional statement is true when P and Q both have the same truth values. In other words, P if and only if Q is another way of saying P implies Q and Q implies P. We can also verify that P biconditional Q, that is P if and only if Q, is same as P implies Q and Q implies P using truth table. We can see that for all the possible values of P and Q, P biconditional Q, P if and only if Q and P implies Q and Q implies P have the same truth values. These are some other common ways to express P if and only if Q. We generally use parentheses to specify the order in which the logical operators in a compound proposition are to be applied. But when these parentheses are not used, we have some precedence for the logical operators. Now let's see another example where we convert an English sentence into a logical expression. Alright, we have to convert this English sentence into a logical expression. So there are many ways to translate this sentence into a logical expression. Even though it is possible to represent the whole sentence by a single propositional variable such as P, it wouldn't be useful when analyzing its meaning or reasoning with it. Instead, we will use propositional variables to represent each sentence part and determine the appropriate logical connectives between them. So let P represent the sentence you can attend the function and Q represent the sentence you are a scientist. R represent the sentence you are a freshman. Now we can write this whole English sentence as the logical expression P implies Q or not R. Next video is gonna be more interesting as we are gonna see some logic puzzles as well as more practice problems. Thank you.